What's up people, this is Libas back with another exciting video, and this is my first tutorial, so please don't judge me if I am wrong in, somehow not able to, explain this to you. So this is going to be the graph explanation and specifically BFS and DFS. So I will be telling you exactly what graph is and how do you apply the BFS and DFS traversal to it. And the second thing that is going to be in this video is going to be the implementation of the graph in C#. You can use any language you want, but I'm choosing C# as my, as my implementation language. So, what a graph is basically, you might see a graph like this, or you might see a graph like that. So, what do you think is the basic difference between these two graphs? The graph on the left, as you can see, has arrows, and these arrows are connected to one another, and actually these arrows are connecting these circles to each other, which means the arrow is connecting one node to another, but it also has a direction. But on the other hand, this graph does not have a direction. So what basically this means is this graph right here is a directed graph, which means that there is a direction from one node to another. So let's say if A is going towards B, the B cannot do the same and go towards A. And similarly, B can go to C, but C cannot go to B. So once we are traversing from B to C, we cannot traverse back to B. On the other hand, if we have a graph like this, but don't mind if I have actually put in the numbers here instead of alphabets. I was just trying to say that make it clear to you guys that no matter you use the numbers or you use alphabets, you can represent nodes by any means you want. So this is called the undirected graph. What this means is that you can go from node 6 to node 4, or you can go from 4 to 6. So that's simple. So the next thing that you need to remember is that when you're seeing the graph, you might notice something very, very strange about graphs. Unlike trees and other ADTs and data structures, that you will notice is that a graph is totally random. So which means that there's no pattern of how these nodes are connected. So the first glance that you get after seeing a graph is that these are the things that you might see in a graph. They are randomly connected nodes, which means that the nodes are connected randomly. B can be connected to C, and B can also be connected to D, or D can be connected to other nodes, and B can be connected to almost every node in the graph. So it's totally random. Represents how our modern world problems look like. So let's say our problems, let's say we are we are just thinking about social network. So in a social network, we have one friend that is connected to another friend, and let's say you are also the friend of that person, but that friend that was friend to another person, that friend is friend of yours. Oh my god, this is confusing. So what basically this means that you have already seen the concept of mutual connection, right? So it's like, you have one mutual friend, and the same mutual friend is a friend of another friend. So it's like a real world problem. The graph basically represents the real problem. Secondly, the most important thing that you see in the graph is that it has data storage. So when you come to the implementation of C#, it's basically using the linked lists, right? And the thing is that you can actually store data into these nodes. So one data can be linked somehow in some respect to another data. So that was the basic thing that you should notice when you see a graph. That's why I actually pointed out these things for you. Now, if you're coming to the operations on graph, the operations on graph are pretty simple. The first thing you might be questioning is that how am I supposed to create a graph like that? So exactly, so first thing you need to do is you have to actually be capable of inserting a node to it. So let's say you insert a first node, and then you somehow insert a second node and point the first node towards that, and then keep adding nodes in a random order. No matter where you want to add a node, you can add. Or maybe you just want to connect A and D, so you need to add an edge too. So the basic operations on the graph are add a vertex. You can add a vertex like that, so you just need to put a vertex here, and you can just add an edge there, so that's how you create an edge. So you can connect that node to this node and then keep doing that on. Also, you can display that vertex. That means display vertex means you can just basically read the data from one vertex and pop out the data from it. Let's say this node was containing, let's say this F node had the name Ali, and the age was 15, sex of male, and different things were there. So you can just display all the data from that vertex. Or you can just simply traverse and print all the graph. This is where the important point comes in. This is basically our video. This is the thing that our whole video is going to be based on. It's basically to traverse the graph. This is where the DFS and the BFS traversal comes from. So let's say you wanted to traverse a graph, but there are different techniques people have actually, came up with. Different computer scientists have came up with this technique to actually traverse a graph. And then one of the most common ones are DFS and BFS. DFS means the depth for search, and the BFS means the breadth for search. Now I will be slowly coming to one of them, one by one. I will slowly covering those topics. So without any further ado, let's get on with our DFS first. So depth for search. I've actually created a graph for you guys here, and as I will be explaining along the way, I will also be showing you the animated part of this. So you will see exactly how the DFS traversal works and how do we exactly traverse a graph. So we have a stack and we have a graph. Now the second thing I wanted to tell you guys is that I am actually making videos based on the advanced data structures. So I'm assuming that you guys have already studied about stacks and queues and other linked lists and other ADTs. So I won't be explaining that part, but I'm pretty sure if you haven't learned about stack, you will be learning a bit about a stack in this video, but you won't be able to grasp exact concept of stack in this video because I'm just directly using it for the implementation of the DFS. So I apologize if I'm speaking too fast for you guys, but I will be improving on that. So what do we need in a DFS traversal is a stack and a graph. Now don't worry about the fact is how this graph is created. We will be creating this graph along the way, so I will teach you exactly how this is done. Right now all you need to do is you have to concentrate on stack. So DFS follows few rules here. So here are the rules. Oh my god, that's a long list. So we will be slowly going through this list and understanding the DFS. The first rule is visit the unvisited vertex and mark it, push it into the stack. What this really means is that, let's say I wanted to start my traversal from one of the nodes. So let's say I choose S here. That's my starting point of the graph. So you can choose any node you want. It can either be B, it can be D, it can be A, or it can be C. You can choose any one, but I'm choosing S here. So now, once I have chosen S, you have to visit that node and you have to mark it. That's what it says, right? And push that node into the stack. So that's our stack right here. So let's say I visit S here. So you can see the S is marked green now. That means it's visited. And now since it's visited, I can push that into the stack. Just like that. And let's say the next node I wanted to visit has to go from a logic. Now this is the more important and the most confusing part that people actually get confused on, is that how am I supposed to visit the next node and what should be the logic? Because there are three nodes connected, and how does S know that what's the next node from it? So we basically work on this logic. Is that, let's say I have my alphabets right here. So I have A, I have B, and I have C. Let's say even I had numbers. So all I can do is I can just sort them into an ascending order, in the program, and then the first node that comes, I can visit that node. So in my case, I have alphabets. So I will sort them. Actually, they're already sorted in your view, but in a program, you need to sort them first. So A, B, C. A comes first, right? Or let's say if there were numbers. So 1, 2, 3. If there was one here, or if there was one here, so the one will be our next node, visiting node. So I will choose A. There you go. A is marked. And now, since it's marked, it will push into the stack right there. Now comes to the next node. Now, since we are on the A, we're talking about the neighbors or adjacent nodes that are connected to A. And in our case, it's just D because there's no other node. If there was, then we will be considering the same logic of visiting the first node that comes into the ascending order. So we only have, unfortunately, D, so we will be just visiting D right up. But the logic is the same. There we go. We mark D. Now, since we have marked D, we'll push it in the stack, and we will be continuing on. Now, if we have B and C, and the B's are going to be the next node, we will mark B and push it into the stack. Now comes the tricky part, where you actually want to see what's the unvisited node, but you can't find any other node because B is marked, and when you're looking for any other node that's connected, that's S. S is already visited. So now comes the part where your stack plays a role. So let's say your B is already visited. So in this case, you need to go back from the graph and you need to check C, because C is a visited node. So in this case, if there's no adjacent node visited in the graph and there's nothing unvisited left, you need to pop that element in which you are currently on. In my case, I on B right now, so I need to pop B now. So I will pop B from the graph, and since I popped B, I came to D, and so you can see that the C is already marked now. That means I actually went to D back, and from D I actually only had the C unvisited because B was already visited, right? So I visited C. You can see that this is how it's actually happening. I popped B and I went to C. Since I visited C now, I will push that into the stack. It's simple. See, that's the second logic. If no unvisited vertex is found, then pop one vertex from stack until a new adjacent vertex is found. Now, since you want to know exactly how you traverse to the graph, like exactly how did you do it, like from S to A, and then A to D, and then D to B, and then we came from B to C, right? So how do we do that? To do that, all you need to do is you just need to pop the elements back from the stack, keep popping until the stack is empty, because we will be following the same logic. You know, if there's no unvisited vertex found, then pop one from the vertex until the new adjacent vertex is found. But we won't be finding any of them because we already visited all of them, right? So we will just keep popping everything. See, we pop that, we pop that, we pop that, that, and the whole graph is empty. Since now we are popping the graph, you know, it's coming to the backwards, right? So we will be, as we are popping the graph, our pop function will be returning what it just popped. So in our case, it can be numbers or it can be alphabets. In our case, it's alphabets. So it will be printing those alphabets line by line. And in this way, we will be traversing to the depth first search. So that was the explanation for depth first search. And with before going actually onto the DFS, the BFS, the breadth first search, I will be implementing the depth first search first, so you can get the clear concept of that first. So let's get on with our C# code.